Hello everyone, my name is Priyansh Kadia and I'm a student from BSc Honours Data Science and Artificial Intelligence program at IIT Guwahati. Today I'm excited to present my term project Cryptographic Analytics, which is a spatio-temporal graph convolution ensemble platform for multi-asset cryptocurrency price forecasting. This is my project for trimester 8. Let's start with the core problem. Cryptocurrency markets are notoriously chaotic. Standard predictive models like LSTMs or ARIMA treat every single cryptocurrency as an isolated asset, but in the real world, crypto assets don't live in isolation. In simple words, think of 100 or maybe more cryptocurrencies as a giant group of friends playing tag on a small playground. If Bitcoin, maybe the biggest kid in the playground, stumbles and falls, all his friends holding hand react immediately. Standard models look at just one kid with blinders on, but our system, it builds a graph neural network that acts like a hawk flying above the playground, watching all the 100 and more kids move together. Technically, we track exactly 107 digital assets across 8 distinct sectors, which is the layer 1s, DeFi, the meme coins, the AI coins, the stable coins, storage, and everything is defined over here in uh, the code file, which is the edge and the edge types Python file. Over here, as you can see, there are different layers with different assets allocated to them. This is layer 1, DeFi, exchange, payment, gaming, privacy, storage, and other type of different ones. Our objective is to predict price direction, the volatility regime, and calibrated 7 to 30 days price trajectories with uncertainty bounds. Now, let's move on to the technologies and database. Uh, I'd like to show you first the system architecture. As you can see, the external data sources like Binance, WebSocket, the Fred macro API, which gives us the Fed rate, CPI, VIX, the CoinGecko API for sentiment. These are the core data sources. Now, I'd like to explain this in really detail, but I'd cut short and use simpler words. Think of this entire system as a 4-story smart factory. The top layer, the live candlesticks are streamed through Binance WebSockets, the macroeconomic series from Fred, and the community sentiment from CoinGecko, as I've already discussed. The second layer, which is the fast API backend, it is managed by 13 SQL Alchemy models, which translates to 14 SQLite and PostgreSQL storing everything from the OHLCV candles to cryptographic proof of performance. Then the third layer is the ML Ensemble forecaster, dual St-Gcn, which is the spatio-temporal graph convolution network. The St-Gcn engine combined with LSTM and neural profit models. So St-Gcn is a flagship model, LSTM is a sequence, and neural profit is a temporal model. And these collectively give us the consensus. And at the bottom, we have a dashboard, which is basically a front end. So it uses the Next.js dashboard, which communicates over 59 REST routes and 4 WebSockets stream, which is not actually really important. But the core software relies on Python, specifically Python 3.11, the PyTorch Geometric, Fast API, SQL Alchemy, Captain, and Optuna. Now, let's move on to data ingestion and feature store. Over here, you can see the feature store class. Let's look at the feature engineering aspect of our project. Feature store class constructs a 24-dimensional feature vector for every single node daily. Now, in simple words, imagine giving every cryptocurrency a daily health checkup card. We measure 24 vital signs. The most important ones, obviously, are the price and volume, which contain the open, high, low, close volume, the OHLCV, the technical health, which is the RSI 14 momentum indicator, the MACD signal, the signal lines. Then we have ATR 14 for volatility, Bollinger bandwidth, ranging from 1-day to 7-day returns, and the 7-day volatility. Then we have market sentiment, as you can see over here, which it is derived from CoinGecko API. The CoinGecko community score, the alternative fear and greed index. Then there's 3-day rolling sentiment mean and momentum, obviously. Then we have macroeconomics like Fed series that includes Fed rate, the CPI inflation, the 10-year break-even inflation, the VIX volatility, So this 24-dimensional feature vector feeds directly into a graph neural network sequence. Now let's move on to the dynamic multi-relational graph and St-Gcn architecture. So over here you can see the entire St-Gcn architecture. Now for the core innovation, how do we build and process the market graph? Over here in graph builder file, you can see the function dynamic graph builder. So it reconstructs a fresh multi-relational graph daily with 3 distinct edge types. The first relation or the zeroth relation is the sector edge. It completely connects the subgraph connecting coins in the same category. Like say the coin is from finance or layer 1. So that's the relation 0. Then moving on to relation 1, which is the market cap edges, connecting the nearest neighbor with the market cap ratio, which is represented as tau. And then we have relation 2, which is correlation edges. Now correlation edges shows the top 5 peers with rolling 30-day Pearson correlation. Now I'll go back to the original figure and try to explain it in simple words. So we have a 30-day sequence of graph snapshots flowing through our neural network. Over here, the linear projection, it projects 24 input features into 32 hidden dimensions in our enterprise mode. So the 24 features get projected to 32 by linear projection. Then we have the STGAT or spatio-temporal GAT. This stacks two RGAT convolution layers with edge condition attention, passing spatial messages across the graph edges. And it has 2 heads per layer. Now moving forward, we have the temporal stack or the temporal encoder. It processes spatial embeddings over 30 time steps using causal TCN or the temporal transformer, which has again 4 heads and 2 layers. In our baseline St-Gcn model, we use a 4-head multitask. We use a 4-head and 3-class direction. So I'll go to the file heads, the heads file. Over here, as you can see, this section shows how we have the 3-class direction of down, neutral, and up, which are the basic requirements. And then we have the 4-class volatility regime, which has these, which is ranging from low, medium, high, and extreme. And then there's auxiliary return volatility regression heads. Then again, in our flagship model, I'll go to the training pipeline. Over here, you can see that we are combining the sector pooling head with dual regression head for expected returns, and we have calibrated uncertainty, which is represented as sigma. Now let's move forward to the composite loss, confidence calibration, and the explainable AI part. So to prevent collapse during the GNN training, we designed a composite loss function. As you can see over here in this particular file, the training pipeline. I'll just explain the math in simple terms. We have the MSE that checks the return accuracy. Then we have a varied regression, which acts like a referee, penalizing the model if it tries to lazy predict the same constant number for every coin. Then there's the list MLE, which is a warm-up gated ranking loss that teaches the model to rank which coin will gain the most. Then moving forward, we have the explainable AI pipeline. In inference pipeline file, we have this section that is basically saying that continuous returns are decoded into calibrated confidence using the Gaussian function, and when confidence exceeds 68%, the signals upgrade themselves to strong up or strong down. That's why we had only 3 heads of down, neutral, and up, and not strong up and strong down. We also done captain integrated gradients over 50 interpolation steps. So over here you can see this the GNN attribution explainer generates SHA-56 cryptographic signatures using the inference attester, which is supposed to be somewhere in this file. And then we have the actual inference attester file, So these predictions cannot be tampered with. It is just back-end hardening. Now I'd like to move on to the results. These are the results from the actual training pipeline, which after the enterprise training pipeline ended, we produced these results. So on the left panel, I'll just zoom it in a bit. We have the training loss progression. It exhibits a clean, stable minimization over 140 epochs from 8.6 to 3.6. Then we have the validation uncertainty. This drops rapidly to 0.62, tracking closely above the theoretical flow that we had set of 0.566. And on the right, we have the validation RMSE that steadily converges to around, I guess, 3.85 over here, as we can see. Then we move on to the equity curve over here. As you can see, over a 550-day test window, which was blindly tested, St-Gcn long-only strategy, the blue line as you can see over here, it achieved a peak return of over 80% and finished down at around negative 10%. Crucially, the crux of it says that it dramatically outperformed the Bitcoin buy and hold benchmark, which plunged down to negative 82%. This proves that a multi-relational graph has successfully preserved capital during severe market crashes. So it's not exactly beating the market, but it can be like an impressive standpoint. And over here you can see the permutation feature importance attribution. This basically shows market capitalization proximity, as you can see over market cap, which is dominating the node attribution, followed by all the volatility indicators, the MACD, RSI 14 and all. And and the key metrics, we have these metrics that we produced from our pipelines. In simple validation, the macro F1 is 0.361 and the annualized Sharpe ratio is 15.533 with an impressive win rate of 81.48 percentage. So also the independent historical backtest, which gave us the realistic Sharpe ratio, which was negative 1.04, which is actually not that great, but we are trying to improve that in our inference pipeline code in the future. So I'll like to honestly wrap up this and present a future roadmap on how we are going to move forward with this project. So to wrap up, the honest reflection of what this project taught me, we can see the gap of Sharpe ratio, which was 15.5, and the out of sample backtest Sharpe, the realistic Sharpe ratio of negative 1.05. So why did this happen? In sample validation, the in-sample validation is like practicing math problems where you have accidentally seen the answer key, and early stopping introducing look-ahead bias. Out-of-sample backtesting is sitting for the unannounced final exam where the real market regimes shift unexpectedly. This teaches us that strict temporal data discipline is vital in financial AI. So this is the ultimate financial machine learning lesson that I'd say. And for the future work, we are going to implement walk-forward cross-validation to implement this look-ahead bias that I had mentioned just now. Then we are going to use migrating GNN graph list execution to we are going to migrate from GNN graph list execution to CUDA GPU acceleration for 10 times speed up, and then this is for the training part only. And then we are going to incorporate on-chain DeFi features like total value logged and active user count. So I'd like to conclude by saying that Cryptograph Analytics, our project, it delivers a simple production-grade 59 root platform bridging graph, deep learning, financial forecasting, explainability, and cryptographic security. I'd like to thank my professors and mentors at IIT Guwahati and for their guidance, and I look forward for the feedback. Thank you.